This is SpaceTime Series 26, Episode 4. Coming up on SpaceTime, uncovering the quantum mysteries of black holes, NASA's angels playing a harp, and 5 new Australian satellites launched by SpaceX. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that the universe's most exotic objects, black holes, can have different masses simultaneously. The mind-bending findings, reported in the journal Physical Review Letters, are based on new calculations looking at the quantum properties of black holes. Black holes are an incredibly unique and fascinating feature of our universe. Put simply, they're singularities of infinite mass in zero volume. Black holes retain only 3 properties: their mass, their spin, and their electric charge. And incredible as it sounds, the laws of gravity as we understand them only predict these 3 properties. The study's lead author, Joshua Fu from the University of Queensland, says the new research suggests that these ultimate gravity worlds' ability to have different masses means they're even more bizarre than previously thought. Fu likes to think of black holes as being created when gravity squeezes a vast amount of matter incredibly densely into a tiny space, creating so much gravitational pull that nothing, not even light, can escape. It's a phenomenon often triggered by the collapse of dying extremely massive stars. However, Fu says until now, scientists haven't deeply investigated whether black holes display some of the weird and wonderful properties and behaviours that are seen in quantum physics. Now, one such behaviour that gets a lot of attention is superpositioning. That's where particles on a quantum scale can exist in multiple states at the same time. Think of a hat in a box. Now, in the quantum world, that hat is both white and black at the same time. It only becomes either white or black when you open the box and look at it. And as weird as it sounds, that sort of experiment using subatomic particles has been proven to be factual. But for black holes, Phil and colleagues wanted to see whether they could have widely different masses at the same time. Turns out they do. Fu says, imagine you're both broad and tall as well as short and skinny all at the same time. Now, it's a situation which is intuitively confusing since you're anchored in the world of traditional physics. But he says this is reality for quantum black holes. Now, to reveal this reality, Phil and colleagues developed a mathematical framework allowing them to place a particle outside a theoretical mass superposed black hole. Mass was looked at specifically because it's a defining feature of a black hole, and it's plausible that a quantum black hole would naturally have mass superposition. Research co-supervisor Magdalena Zich says that this research is in fact reinforcing conjectures first raised by some of the pioneers of quantum physics. This work shows that the very early hypotheses of Jacob Bekenstein, an American-Israeli theoretical physicist who made fundamental contributions to the foundation of black hole thermodynamics, were correct. Bekenstein postulated that black holes can only have masses that were of certain values. That is, they need to fall within certain specific bands or ratios. It's the same way as how energy levels work in an atom. Electrons around the nucleus can only be in certain specific energy levels. The new modelling shows that these superposed masses were in fact in certain determined bands or ratios, just as predicted by Bekenstein. Now, it's important to note that the authors didn't assume any such pattern going in, so the fact that they found a pattern came as somewhat of a surprise. Fu says the findings showed that the universe is revealing itself to be even more strange, more mysterious, and more fascinating than most people could ever have imagined.
There's usually a distinction made between astrophysical black holes, which are the ones that we look with our telescope into the sky and observe their signatures by various means. And then there's theoretical black holes, which are basically the kinds of solutions to Einstein's theory of gravity that the mass equations solve, and we can construct these theoretical black holes that behave as we would expect them to behave in outer space, but we can more easily manipulate their properties and study some weird phenomena and do crazy things with them.
And it can be on a really small scale.
Yeah, exactly. So as you may know, black hole is a region of space where mass is compacted into a tiny, dense region such that the gravity is so strong that nothing can escape the pull of that region of space. So they're black holes because even light can't escape the gravitational pull of these objects.
It's a lot like me getting to a wetsuit when I go surfing. I know the feeling. Now, when I went to university, I was told that black holes only really have three properties: mass, spin, and electric charge. Now, your research is suggesting that one of those properties is quite variable. That's something that I thought only neutrinos could do. Tell me about it all.
Yeah, well, if we believe quantum mechanics is true, then quantum mechanics should apply to the whole universe, and that includes objects that are very large. We should expect that even gravity can behave quantumly, and that includes objects described by gravity, such as black holes. And so a unusual and counterintuitive property of quantum mechanics that we know is that objects can possess multiple properties simultaneously, and this principle is known as the superposition principle. So what we sought to do was to study the effects and the phenomena produced by black holes when they have a mass that is in a superposition of different values simultaneously. And the reason why we're interested in this is because a lot of interesting physics usually comes about when we study effects at the intersection of quantum mechanics and gravity. So we basically applied the principle of superposition, a very quantum mechanical effect, to the astronomical scale of a black hole. And that's the kind of intersection of these two theories that usually gives rise to new insight into physics that is unexpected and unexplored.
And there were properties you found that had been predicted in the relativistic world, which also turned up in the quantum world as well.
Yeah, exactly. So in the 80s, a pioneer of quantum gravity, so-called, the field of quantum gravity, Jacob Bekenstein, basically came up with this idea that if black holes are actually quantum objects, then they should behave in a similar manner to how quantum objects behave at the microscopic scale, the atomic scale. So he treated a black hole as if it were an atom. And an atom, as we know from quantum physics, has certain properties, certain allowed values of its energy, for example, has certain allowed values of its momentum and its spin. And so Bekenstein reasoned that if black holes are truly quantum, then they should behave like atoms. And so an atom, being a quantum object, can also exist in a superposition of, for example, energies or different momenta. So it can have different masses, different energies simultaneously. And so we reasoned, okay, if that's the case, then we should extend Bekenstein's conjecture to black holes such that they should be able to be in a superposition of masses or energies. And what we did was we created this black hole, this theoretical black hole in a superposition of masses, and we stuck a particle outside the black hole. And the particle can sort of interact with the black hole and the environment that the black hole produces, the extreme gravitational environment that the black hole produces. And we found that the particle reacts to this environment in a very particular way that actually gives us a signature of Bekenstein's original idea that black holes should have these special values of the mass, these discrete values that it can allowably have. And so we basically, without assuming anything about Bekenstein's conjecture, we were able to independently corroborate or independently verify his original ideas about what black holes should behave like in a theory where black holes are actually quantum objects. And so that's the main result of our paper.
When you extrapolate that out, does that mean when we look at a black hole and we predict its mass by its effect on something orbiting around it, does that mean we can't trust that anymore?
I would say that the allowed values of the mass of a black hole, they the spacing between the different masses would be minute. They would be on the level of the Planck scale, the so-called Planck scale, which is just basically a very tiny number. So when we're dealing with quantum objects, we have this length scale known as the Planck scale, and this basically is a measure of how the discrete masses of the black hole can exist within. So the difference between certain allowed values of the mass, I don't think they would be necessarily observable, But in principle, the fact that they take on a discrete value is still a drastic departure from what we would typically understand how mass should function. We would expect mass to be a continuous parameter. You can have a black hole that's anywhere between 10 kilograms and 20 kilograms. But what this is saying is, what Bekenstein was saying is that, no, the black hole can actually only have a mass that's 10 kilograms or 12 kilograms or 15 kilograms and so on. So its effect on perhaps telescopic or astronomical observations probably wouldn't account for much. Yeah.
What inspired you guys to do this research?
Well, the sort of frontier of theoretical physics at the moment is this sort of decades-long pursuit to unify gravity, which is Einstein's theory of how mass curves space and how objects with mass attract each other and how they move through space, and quantum mechanics, which is the theory of how things move and behave at the subatomic level. And so this is sort of this holy grail of theoretical physics. But this problem has proven to be very hard, and so physicists have sought to approach this problem from sort of the bottom up, from taking what we know about gravity and what we know about quantum theory and sort of putting them on top of each other, so to speak. So to study systems, study different kinds of environments where these two theories and the effects that they produce overlap a lot. And that's how we hope to gain further insight into how eventually one might completely unify quantum mechanics with gravity to come up with a theory of quantum gravity. And so there's been a significant history in how pioneers of this field have derived new effects and new phenomena by studying black holes, which are on the one hand these extreme gravitational environments, with quantum mechanics. For example, considering how particles behave around black holes and so on. So this is what motivated us. Yeah.
So do you like your universe loopy or stringy?
Well,
Because I got to tell you, I'm a loop quantum gravity sort of guy.
Well, I guess if we want to sort of take an approach to science that we seek empirical evidence for our theories and we want to eventually confirm our theories through experiment, then in reality, string theory has taken on some hard times recently for its basically inability to be verified in, say, for example, experiments. As for loop quantum gravity, there are people who work in this area who have conjectured similar ideas to our paper that sort of fall out of the theory of loop quantum gravity. And so if I had to pick one or the other, I would probably lean towards loop quantum gravity because because predictions like black holes with superpositions of masses can sort of fall out eventually from the loop quantum gravity perspective. Yeah.
When you look at the whole idea of gravity, is it a force or is it simply an effect? Is there an actual particle of force called a graviton?
Yeah, well, that's another line of research that is being hotly pursued at the moment, which is this search for the elusive graviton. And so there are four fundamental forces in nature, and gravity is by far the weakest of these forces. And so it's been very hard to detect the presence of this graviton. So I should mention that these four fundamental forces, which we know are gravity, electromagnetism, and the weak and strong nuclear forces, they're all mediated, so they're carried by fundamental particles. And so we've observed the fundamental particles that are associated with the three other forces, electromagnetism and the weak and strong nuclear forces, but we haven't been able to detect this elusive graviton. But actually, in a research field adjacent to mine, there have been some very exciting experimental proposals that also consider particles in superposition that would give evidence. If the experiment were performed and done, then this experiment would give evidence that such a graviton exists and that the graviton is the force carrying particle of gravity. That was a very roundabout way.
I want to see that experiment.
Yeah. Well, as you'd expect, it's very hard to get. You need objects, particles that are massive enough to produce their own gravitational field, but are small enough so that you can put them in superposition. So there's this very fine balance between creating these kinds of experiments where you need particles that actually can emit gravitons and interact with each other.
That's Joshua Fu from the University of Queensland. And this is SpaceTime. Still to come, They say angels don't play with HAARP. Well, that's proven to be wrong because NASA's angels have just played with HAARP. And 5 new Australian satellites launched by SpaceX as part of the Transporter 6 mission. All that and more still to come on SpaceTime. NASA has used a powerful HAARP array in the remote north of Alaska to study an asteroid. The asteroid 2010 is estimated to be about 152 metres wide, and it was making a pass of the Earth at a distance of about 769,000 kilometres. The experiment used the powerful HAARP transmitter array to send long wavelength radio signals into the asteroid to learn about its internal structure as part of efforts to defend Earth from future major asteroid collisions. HAARP stands for High Frequency Active Auroral Research Program. It was initiated as an ionospheric research project by the United States Air Force and Navy and DARPA, the Defence Advanced Research Projects Agency. HAARP was designed and built by British Aerospace to analyse the ionosphere and investigate the potential for developing ionospheric enhancement technology both for radio communications and for surveillance. Think of Australia's own Jindalee over-the-horizon radar system. However, HAARP has also become a major target for conspiracy theorists who insist that it's a clandestine operation designed to weaponize weather. They allege the system's radio frequencies manipulate the surrounding environment, changing weather patterns over large areas. They say this also unnaturally impacts the Earth's upper atmosphere and it jams all global communication systems. The conspiracy theorists also claim it disrupts human mental processes, interferes with wildlife migration patterns, and can even negatively affect your health. Scientists say those pushing these conspiracy theories are uninformed, as the claims made fall well outside the abilities of the facility, if not the scope of natural science. The results of the asteroid experiment are now being analysed by NASA's Jet Propulsion Laboratory in Pasadena, California. It's the first time an asteroid observation was attempted at such low frequencies, and it shows the value of HAARP as a potential future research tool for the study of near-Earth objects. There are several projects out there which can quickly detect asteroids, determine their orbit and shape, and even image their surfaces, either with optical telescopes or planetary radar setups, such as NASA's Deep Space Communications Network, which includes large, very sensitive radio antennas in California, Spain, and Australia. The HAARP experiment follows tests last January and October when scientists bounced long wavelength signals off the Moon in preparation for this week's experiment. However, these radar imaging programs can't provide information about an asteroid's internal structure, such as whether it's a solid chunk of rock or a loosely bound pile of stones and dust. That's important because understanding the makeup of an asteroid's interior, especially if a large asteroid, one big enough to cause major damage on Earth, can increase the chances of an effective defense. And knowing the distribution of mass inside a dangerous asteroid will also help scientists targeting devices designed to deflect an asteroid away from Earth. The Deep Space Network uses signals of short wavelengths, which bounce off the surface and provide high-quality external images, but don't penetrate an object. It's the long wavelength radio signals such as those used by HAARP which can reveal the interior. HAARP's 3 powerful generators transmitted chirping signals of long wavelengths for some 12 hours. The University of New Mexico Long Wavelength Array near Socorro and the Owens Valley Radio Observatory Long Wavelength Array near Bishop, California were also involved in the experiment. This test's also being seen as a dry run for a future experiment involving the asteroid Apophis. Apophis will make its closest approach to Earth on April the 13th, 2029. During that close encounter, Apophis will pass just 32,000 kilometres above the Earth. That's closer than many satellites. The 400-metre-wide space rock, discovered back in 2004, was initially thought to pose a serious threat to Earth, depending on how Earth's gravity interacted with it, with some scenarios showing a likely impact with Earth either in 2032 or 2068. The good news is more precise details on its orbit and trajectory have now ruled out both dates. But Apophis remains a potentially hazardous object, one we need to keep an eye on. This is SpaceTime. Still to come, SpaceX starts off the new year by launching 5 Australian satellites. And later in the science report, justice finally for nuclear physicist Robert Oppenheimer. All that and more still to come on SpaceTime. SpaceX has started off the new year setting a new launch record as the Falcon 9 rocket sends 114 satellites into orbit aboard the Transporter 6 mission, including 5 Australian spacecraft. The dedicated small-sat rideshare flight from Cape Canaveral Space Launch Complex 40 involved no less than 82 individual deployments into sun-synchronous orbits between 525 and 550 kilometres in altitude. It was the 15th flight for the same Falcon 9 core stage, which again returned to Earth successfully, touching down on Cape Canaveral's landing zone 1 just 8 minutes after launch.
Stage 1 LOX load complete.
So with that call out, liquid oxygen loading is complete on the first stage. We'll hear a similar call out on the second stage.
Stage 2 LOX load is complete.
So with that, we are fully loaded with about 1 million pounds of propellant on the vehicle. Some clouds coming out from the vehicle. These clouds are coming from the transporter erector lines. Now, the transporter erector provides the propellants to the vehicle. We're just clearing out the lines and the cold
Gas close-ups.
The cold oxygen that is in those lines ends up coming into contact with the moist Florida air and produces literal clouds around the vehicle. Coming up, next major milestone will be Falcon 9's transition into startup. That means that the flight computers on board the first and second stage will have taken over the launch countdown, and they'll continue to have control of the vehicle through the rest of the mission. Next major milestone will be the launch director giving their final go for launch.
Go for launch.
And with that call, all systems go for launch as this Falcon 9 takes the Transporter 6 mission to orbit.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff.
Vehicle's pitching downrange.
Stage 1 chamber pressure is down.
Falcon 9 clearing the tower at Space Launch Complex 40 and making its way to orbit. We are currently throttling down the Merlin 1D engines on the first stage in preparation for the point of max Q. That's the point of maximum aerodynamic pressure.
Falcon 9 is supersonic.
Maximum aerodynamic pressure is the point when the highest stresses are experienced by the vehicle during the ascent.
Max Q.
With that, we are through the highest stresses on the vehicle. Coming up, we've got several events back to back. The first of those is main engine cutoff, or MECO. There will shut down the 9 Merlin 1D engines in preparation for stage separation. Stage separation is where pneumatic pushers will separate the first and second stages. And then we'll have second engine start number 1. We just heard a call out for MVAC chill-in, so we've begun chilling in the turbopumps in preparation to start the Merlin vacuum engine on the second stage. While the second stage engine is burning, the first stage will be performing a flip maneuver, and then it will do a boost back burn. That boost back burn will ignite 3 of the Merlin 1D engines to make the first stage's way back towards land, since we are attempting a land landing today with this first stage. So again, those events back to back, MECO, stage separation, first stage flip, second engine start number 1, and then the boost back burn.
Stage 1 shutdown.
Stage separation confirmed.
MVAC ignition.
Stage 1 boost back startup.
So there is those 5 events, the first stage boosting away and the second stage continuing to burn. Now this burn on the first stage will last about 47 seconds, and the second stage is going to continue burning for a while. It will complete its burn until the T+8 minutes and 20 or so second mark. Shortly after the boost back burn ends, the next major milestone will be fairing separation.
Stage 1 boost back shutdown.
So there is successful shutdown of the boost back burn. Some pulses there from the attitude control system. We use nitrogen gas as our attitude control medium, and it helps us keep pointed in the correct direction. The bursts firing on the first stage as we are also deploying our grid
Fairing
fins.
separation confirmed.
We will be attempting to recover both of these fairing halves once they land back in the water on a recovery vessel named Bob. We're in the first of 2 Merlin vacuum burns. First burn will last until about the T+8 minute and 20-second mark. Next major milestone will be the first stage's entry burn. Now, we execute the entry burn in order to slow down the first stage before hitting the densest parts of the Earth's atmosphere.
Vehicles are on a nominal trajectory.
Without that burn, we'd be only using the atmosphere to slow down the Falcon 9, and that puts a lot of extra stresses on the rocket. So we ignite 3 of those Merlin 1D engines to slow down as we hit the thickest parts of the Earth's atmosphere. We had an on-time liftoff, 9:56 a.m. Eastern Time from Cape Canaveral Space Force Station. And we're carrying the Transporter 6 mission on the second stage right now. It's SpaceX's 6th dedicated small-sat rideshare program and our first mission of 2023. We're targeting at least 3 dedicated rideshare flights to sun-synchronous orbit per year. And we also offer opportunities to ride to orbit on our Starlink missions, which launch about once a week. Now, these small sats can ride to space on our Falcon 9, Falcon Heavy, the Starship vehicle in the not-too-distant future. The grid fins have deployed on the first stage. We've got 4 of these hypersonic grid fins near the top of the stage. And once we get into the thicker parts of the atmosphere, it's only the grid fins that do the steering to make our way back to landing zone 1. Next major event, that's the first stage's entry burn, but we'll ignite 3 of the Merlin 1D engines.
Stage 2 FTS has saved.
That
Stage 1 entry burn startup.
drop off dramatically as the entry burn is slowing us down. Pretty quick burn. This one will last about 20 or so seconds.
Nominal trajectory.
Stage 1 entry burn shutdown.
And there is successful shutdown of those Merlin engines. Now, as we are slowing down, re-entering the Earth's atmosphere, if you're in the Florida area, you may hear some sonic booms.
Stage 1 FTS has saved.
We are attempting to recover this booster for the 15th time today, targeting this landing at landing zone 1. We've got just one more burn, which is the landing burn on the first stage. We'll ignite just a single center Merlin engine. That'll happen just before touchdown.
Stage 1 transonic.
Stage 1, the center engine
Stage
has
1 landing
ignited.
burn.
We'll expect to see the 4
Stage
landing
2
legs
terminal
deploy
guidance.
for a soft touchdown at landing zone 1. Now, during this, we'll also hear a call out of second engine cutoff on the second stage.
Stage 1 landing leg deploy.
Seco.
Stage 1 landing confirmed.
So landing is complete. We also heard a call out there for SECO.
Nominal parking orbit.
SECO is second engine cutoff number 1. We just heard a call out as well for nominal parking orbit. And with that, we have landed the Falcon 9. It's our 161st landing of an orbital class rocket. This booster's 15th. Now, coming up, our next major event will be in about 45 minutes. That is for second engine start number 2. And that'll be followed shortly by the first 35 payload deployment events.
Included in the payload were 5 60-kilogram air traffic management system prototype satellites built by Canberra company Skycraft as part of a 3-month proof of concept test program for Air Services Australia. If successful, Skycraft plan on developing a global constellation of more than 200 satellites over the next 2 years, providing air traffic control management services for pilots. The system's designed to provide aircraft with traffic management coverage as they cross remote areas, places like oceans and deserts, where surveillance gaps exist in global communication systems. The Skycraft satellites are using local Australian technology and equipment, ranging from printed circuit boards produced in Newcastle, satellite frames built in Wodonga, and thermal finishes applied in Queen Anne. The largest single customer aboard the Transporter 6 mission was Planet. It had 36 SuperDove Earth imaging CubeSats in the payload. This increases Planet's satellite constellation to over 500. Also included in the manifest were 12 Spacebee Internet of Things satellites for SpaceX-owned Swarm Technologies. Spire Global set up 6 Lima CubeSats for its growing satellite constellation, monitoring maritime and aviation traffic using ADS-B technology. Also aboard Transporter 6 were 4 Satellogic Earth imaging satellites, 4 Cleos radio frequency intelligence gathering satellites for Luxembourg-based Spaceflight Incorporated. These will be used to search out hidden and illegal activities from space. There were 3 synthetic aperture radar imaging satellites deployed for ICI, 2 satellite phone communications CubeSats for Link, 2 synthetic aperture radar imaging satellites for Umbra. Then there was the Gamma Alpha solar cell technology test satellite for French company Gamma, the Bro 8 radio frequency intelligence gathering satellite for French startup Unseen Labs, Electro-optical infrared weather systems included a new technology demonstration CubeSat for the US Space Force's Space Systems Command. Then there's NSLCom's quaintly named BeetleSat. It's a 9-kilogram spacecraft designed to provide high-throughput telecommunications services, transmitting at rates of up to 2 gigabits per second, using innovative new software-defined radio technology and a deployable antenna communications payload. The last satellite to be deployed was the EOSat-1, EOSTA's first agriculturally focused analytics satellite. It's the first of 7 spacecraft being built by Dragonfly to monitor the health and growth of crops. The Transporter-6 mission also included several orbital transfer vehicles, or space tugs. These were all fitted with their own payloads, which were designed to be deployed later. They included 2 deorbit ion space tugs, each carrying a series of small satellite payloads, including NPC Space Mine's Futura 1 and Futura 2, their 3 and 6 unit CubeSats designed to demonstrate the company's new CubeSat platforms, as well as Arctica, an innovative deorbiting sail designed to accelerate the orbital decay of spacecraft, thereby reducing the amount of space junk currently circling the Earth. Also aboard were 4 5-kilogram CubeSats for Astrocast, as well as the Sharjah Sat-1 X-ray space telescope, which will detect hard X-rays from very bright astronomical X-ray sources with a secondary payload using a dual camera system for Earth imaging. The Tel Aviv University's TauSat-2 research satellite was also included. It's carrying a scientific payload of light-emitting diodes that will be used to conduct optical tracking experiments looking for miniature objects in space. It also included an S-band transmitter that's aimed at demonstrating a novel new communications protocol in various signal-to-noise regimes. There's the 4-kilogram Kelpie-1 3-unit CubeSat built by AAC Clyde Space. It's designed to deliver automatic identification system data. The Drago 2 CubeSat is a project by the Institute of Astrophysics in the Canary Islands to develop a compact multispectral shortwave infrared Earth observation satellite capable of high-resolution images. The Milan Polytechnic set up the Genogo 2 experimental space propulsion system so that it can be tested in orbit. Then there was Cryptosat-2, an enhanced version of a prototype nanosatellite developed by Cryptosat for secure cryptographic applications. It can be used for things like electronic voting, trusted random beacons, and verifiable delay enforcement for smart contacts. Other space tugs sent aboard the Transporter-6 flight include Launch's first orbital transfer vehicle and the second momentous Vigoride orbital service vehicle, which this time hosted Caltech's space-based solar power project payload and also deployed a satellite carrying the Osmosis Zeus 1 payload. Just a few days earlier, SpaceX launched a new Earth Resources satellite for Israel from the Vandenberg Space Force base in California. The Earth Resources Observation System's NG-3 or Eros C3 Earth imaging satellite was launched aboard a Falcon 9 rocket into an unusual retrograde orbit, meaning it circles the planet against the direction of Earth's rotation. Designed by Israel Aircraft Industries and based on an OPSAT 3000 class satellite platform, the spacecraft has a panchromatic imagery resolution of 30 centimeters and multispectral imagery down to 60 centimeters. The 400-kilogram satellite is owned and operated by EmidSat International, which was founded by Israeli Aircraft Industries, ELOP and Core Software Technologies in 1997, and now also includes both the Italian Space Agency and Telespazio. The first 2 Eros satellites, Eros A and B, were launched aboard Russian Star 1 rockets from Siberia back in the years 2000 and 2006. But the Eros C3 is part of a new generation constellation, which also includes the old Eros C1 and C2, which were repurposed from the Opheg 11 and 16 Israeli spy satellites. These were launched aboard Israeli Shevet 2 Comet 3-stage rockets from the Palomar Chim Air Base near Tel Aviv in 2016 and 2020. 3 more satellites are expected to join the Eros NG constellation, including the Eros C4, as well as the Erosar 1 and 2, both of which will operate in the X-band spectrum. Following the launch and after MECO or main engine cutoff and stage separation, the Falcon 9 core stage performed an RTLS, or return to launch site landing, successfully touching down on landing zone 4, just a few hundred meters from Space Launch Complex 4 East, where it had taken off just 7.5 minutes earlier. This is SpaceTime. that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.